Hello, community. Let's fine-tune our own co-pilot, our own coding LLM. So we will create here a very personal generative AI for code generation, a code generator LLM, or simply a code LLM. And we will do this here with classical fine-tuning and a PEFT LoRA tuning. But let's start at the beginning. We need our training data set, we need content. So we go out and I will show you here the code. We will go to the GitHub repos and have here specific GitHub repos chosen. From those GitHub repos, we will create our own data set of code, our code sequences that will form here the training base for our fine-tuning. I will show you the code how to do this. And then, of course, the beauty, if we do it ourselves, is we choose the best GitHub repos out there for our specific task. So this means, if you think about all the GitHub repos here as a little 3D cubes, I don't need here from thousands and thousands of repos to extract here, and this is the little dust you see in this image here, the code. I don't need 1,000 repos. And maybe on those 1,000 repos are on 100 different topics. I'm focusing here for my task, for my actual topic. Let's say it is how to fine-tune PEFT models. And I just want to have the best 3 or the best 10 GitHub repos on this topic that are up to date, updated just an hour ago. So we will do today a full fine-tuning here of a pre-trained coding LLM, and we will use StarCoder as our pre-trained CODE-LLM. And we will use here some beauties like flash attention version 2 and a fully shorted data parallel processing, and I will explain to you why we need this. And of course, this is maybe why you're here. We will do the same then in a PEFT LoRA fine-tuning on our code data set. We will even go with some quantized LoRA or some multiple LoRA adapters. And of course, we're going to use here Hugging Face Accelerate or DeepSpeed. And we will go through the code exactly. I will give you here the code base so you can download it and experience this on your specific tasks. Great, let's start. Step 1. We have to understand, our foundation is the pre-trained LLM. This is StarCoder. How is it input data structure been trained on? What is the architecture of the model? How we can optimize this in a later fine-tuning step or in a LoRA step. Let us use here in Hugging Face Spaces here this demo to find out what StarCoder is doing. So this is a fine-tuned version of the StarCoder base model, specifically focused on Python, also strong performance in other languages, but we are talking about Python here. So I choose here StarCoder, and this is my input. I have here a very simple function, and as you can see here, I program something, and then I just say, hey, fill here. So I have this code, and I do not know how to do this if the length of the list 1 is bigger than the length of the list 2. How do I cope with this? I say generate. Oops. And here is our output. And you see here, this was here a code completion task performed here by StarCoder. Or let's take another example for StarCoder. We say, hey, our input is here xtrain, ytrain, xtest, ytest, train, test, split functionality, train a logistic regression model, predict the labels on the test set, and compute the accuracy score. And we say calculate. And you say, wow. Okay, so we have here a logistic regression model. Okay, logistic regression. Then a random forest model, a support vector machine model, a k-nearest neighbor model, a decision tree model, a multi-layer perceptron model. So you see, this is, now we understand what StarCoder can do, and we want to optimize StarCoder. We have here our GitHub repos somewhere on the servers worldwide, and we extract here the code information for specific repos. We put it here on our compute infrastructure. we have StarCoder as the pre-trained model, and now we do the fine-tuning on our specific code extractor data to have an expert system, so a very specific coding system, and not a coding system like Microsoft GitHub Copilot, which is everything to everybody in this world. We will have an expert coding system that is really actual. So, why I show you here an image of some distributed GPU computing. Now, let's have just a fly over the GPU, or in general, the minimum GPU memory requirements for the full classical fine-tuning. What we see is we end up here, or if you just think about here what we need as a minimum, you come close to here a 250 gigabyte of GPU memory. Remember, we are using StarCoder 15 billion pre-trainable parameter model. Great. And we haven't even considered here intermediate activation checkpointing, flash attention to, gradient checkpointing. So we even get here a boundary condition on the memory occupied per GPU in our GPU node. And now the memory per GPU is about 70 to 78 gigabytes. So this means the fine-tuning of StarCoder 15B, we will use here a compute node with 8 times an A100 80 gigabyte GPU. So 8 GPUs. So you see why we need distributed computing. And we will use every optimization we can imagine. We will use here Pytorch fully sharded data parallel technique. And now you see why I'm talking about distributed computing if we talk about full fine-tuning. This will change if we apply LoRA or quantized LoRA. Now, if you want to understand what is gradient checkpointing, I ask here Bart to explain this in a simple way. And if you want to find out how much VRAM you need here to train and perform big model inference, we have here Hugging Face Accelerate memory usage. So you just put in here a specific Hugging Face model. I take here Zephyr, the 7 billion in the beta version. I say library auto, model precision. I click on all 4 and I say calculate the memory usage, and you will get now the memory usage depending here on the precision, the numerical precision you have. So for float 32, for the full precision, you have here the largest layer, the total size that you need here. We are talking here about VRAM, and the training using here an ADAM optimizer. So training here of an LLM model, they say with an ADAM optimizer is about 4 times the size here of the normal size. So you see we floating 32 for a Zephyr 7B beta. We need here about 110 gigabytes. If I go with BrainFloat 16, I need half, 55 gigabytes. And if I use now quantization, I have a quantization of my values going down to an integer 8. Now I'm at 28 gigabytes VRAM. And if I go down here with an integer 4 optimization, I'm down to about 14 gigabyte of VRAM calculated by Hugging Face Spaces, Hugging Face Accelerate. And whatever Hugging Face model you put in here, it gives you a rough estimate of the total size. And here, if you do the training using an ADAM optimizer for your VRAM. But you might say, hey, wait a minute. Yesterday, I mean, it is yesterday from my perspective, recording this video, there was OpenAI Development Day, and they said, hey, we can build our own little GPTs, where we have a GPT builder, like here. We say, hey, we have the name of the new GPT, little GPT in our GPT store. We have a description, what we want this to do. We give it an instruction, and you see, hey, this little GPT is already being created here by OpenAI. And now you see the knowledge integration. So the update, for example, we can upload files. This is great. But remember, even the GPT-4 Turbo with 128K content length has a very limited token length. So if you want to update, I don't know, 100 GitHub repos, you will run into troubles. And by the way, even if we click on Code Interpreter, and you know that this code interpreter, the very latest code interpreter of GPT-4 Turbo, will have a knowledge cutoff in April 23. So I lose everything that happened this summer is not included in my code interpreter. And this year seems not to be the fine-tuning, but this year seems to be something like a RAG process where I integrate here some files in addition to the knowledge of the code interpreter. So I cannot feed in my complete updated GitHubs, and the code interpreter is still half a year old, even today, before it comes out. So this is a problem we have to face, and this is why I do this video on fine-tuning your own code interpreter. Again, updated knowledge, GPT Turbo, April 23. Code interpreter has also a knowledge cutoff of April 23. And if you want to have here every knowledge in the last half year, and there was a lot of paper, and if you're into research AI, like I am, and you experience code sequences from the authors of this research paper that are just 3 days old, or 5 days old, or 12 hours old on their GitHub repo, you have no way to use a classical OpenAI code interpreter to integrate here the latest results from last week. So this is the reason why I show you how to fine-tune your model that you choose on the new data set. So we have here now that from April 23 to November 23, this is the data set that we want, and we want to have this in a fine-tuned version so that it is really integrated into the reasoning of our new CODE-LLM. I want to show you here specific code, and I've chosen this code very carefully. And I want to show you two professionals. They both work for Hugging Face. And I go here with two Hugging Face wizards, I call them, with Sayak Paul and Saurabh Mangulkar. And they have public repos on GitHub, and they update their code. This is very beautiful. So if you come back in 1 or 2 months, you will have updates, and they have public repos. And this is why I've chosen their particular code implementation. Great. Yeah, and if you like, hey, why not give them a like, a hug, or a follow, or whatever? I think they would appreciate it. Let us start at first to extract here from GitHub here all the public repos that we are allowed to have a look at. So we follow here in this GitHub here, Sayak Paul, and as you see, we have here the organization Hugging Face, and we take here the public repos. So we have here a function get repos, fetches the repository for a particular GitHub user. We have here Hugging Face. So this is it. Then we mirror here. We make a local clone of the repo. Done. We clone here this with a sub process. Then we mirror the repos. Great. And this is it. And now we have our repos. Now, from those repos that we have now downloaded, we have to prepare the dataset. So we just go to the next file here, prepare dataset.python. And as you can see here, we are working here with the notebook format. We import here the read and the no convert command. We have here Hugging Face Hub, yeah, and again, sub-processing, beautiful. So the dataset, yes, we have created this. We serialize it in chunks, beautiful. And then we say, okay, from all this information in the GitHub repos, we do not want the following: images, PNG, JPEGs, or GIFs. We do not want video because we just want to extract the code. And we do not want any sources where we have a PDF or some doc file or some PowerPoint slides. We want to extract the code. So anything else? Yes, yes, yes. Others? Yes, great. So all the anti-formats that we do not want, we have defined. So now we move all the files, matching here the file format to a folder, and upload, for example, this folder to the Hugging Face hub or whatever is yours particular drive. Yes, yes, yes. Then we filter the code cells, filters the code cells with the shell commands, with respect to the shell commands, and then you process the file. Open file path, code, notebook. Now reads the content here of the notebook, and then you're not going to believe it. For a cell in code cell string plus equal the source code in the cell. So this is how we do it. Then you have here a function read all our repo files, reads the files from the locally cloned repos. Yes, beautiful. Find all the files within the directories, process the files sequentially, and here you have it. This is it. So now we extracted all the information, all the code-specific information from all the different repos. Now, if you want to see this, the result is here on Hugging Face. Here you have here the Hugging Face stack version 1. So what we achieved, let's have a look at this, where we have here accelerate setup. Yeah, let's go here. So we have here our public repo. Then we go here, for example, for the accelerate repo, and we have here our setup Python command. And now here you have the code of this Python file cleaned up, so ready to be used within our fine-tuning. And there we have close to 6,000 rows, so you see where we are going with this information. However, what I would like to show you, let's say what is the easiest one, well, maybe not this. Here we go. If you do not know what is happening here, now very easy, just copy this. So I copy here the Python file, and if I want to analyze this code, I copy it in, and let's see what's happening. And now GPT-4 Code Interpreter, the classical code interpreter, tells me exactly what it is. Import statement, what is here the OS model, what is a sub-process, what is here pooling from multi-processing, GitHub package, GitHub API, constants, and then explains here what each function does. Get the repos, gives you an explanation. So whenever you are stuck, this is a good way. Use the help that is provided here with the knowledge of GPT-4. Gives you here the main guard. Then I have here in my customization that I want to have this analysis and consideration about security, error handling, performance, dependencies, and best practices, potential improvements. And if you even want to go further, and if you have a particular wish, you would like to optimize this code. Can you optimize this code sequence you just analyzed? And certainly, the code can be optimized in several ways. Reduce the API calls, improve the error handling, limit the number of concurrent. Use Git Python for the cloning, efficiency, skip already cloned repository, and it gives you here an optimized code version. Now you have to check very carefully if this is really an improvement, but you see it helps you in understanding code, it helps you in optimizing the code. And if you give this GPT-4 code interpreter directions how you want the code optimized, it is also to perform this functionality. So tells you, hey, these are some ideas I have, and you can immediately try it out if this is an optimization, if you need optimization. Beautiful. This was it to extract our data, to clean our data, to build our data sets for the fine-tuning. And now we're ready for the next step. So our next step that we have now the data set for our fine-tuning created, we have to optimize our complete system to the max. We use everything out of the book that we know. We have to bring down the memory requirement. This thing should run fast and should not cost us a house. So we have a lot of possibilities. We have a data parallelism, a tensor parallelism, a pipeline parallelism. And if you combine all those three into a 3D parallelism paradigm, welcome, this is exactly what we are going to use. So, DeepSpeed. I will focus on DeepSpeed and FSDP. So what is DeepSpeed? It is beautifully integrated already for us. It is done the code. We just go to the Hugging Face Accelerate library, a high-performance library for training a large LLM on multiple GPUs, a distributed system, or even TPUs, tensor processing units from Google. Hugging Face Accelerate integrate here our DeepSpeed zero stage 3 technique, offload the computation of gradients to CPU or GPU memory, further reducing the memory footprint of training. If you want to get an idea of DeepSpeed, here's something by Bart. Great. Now, we need to configure your infrastructure, your computer infrastructure, exactly here for DeepSpeed. And this normally happens here, not in a YAML file. And this is a YAML ain't a markup language file, is a text-based data serialization format that is commonly used for configuration files. And here, this is one possible that you see with a short explanation what it is doing. It just tells the system what to do, which type to use, DeepSpeed, where we are with our types, brain float, float 16, the optimizer we want to use. This is the AtomW, the learning rate, the rate decay, the scalar, all the parameter. We just tell them with the zero optimization stage 3, offload optimizer, offload parameter, everything tells us, and I will show you our exactly DeepSpeed YAML file for our code. But of course, now more than a year old, we have here also in the Accelerate library integrated here another distributed training technique, especially for Pytorch, the Pytorch fully sharded data parallelism. And if you don't know the term sharding, then a term borrowed from the databases where a large database is partitioned or sharded into smaller, more manageable pieces. Beautiful. So sharded refers to the partitioning of a model internal states, its parameters, its gradients, and its optimizer states across the memory of multiple GPUs. So this division allows each GPU to store and manage only a rather small portion of the model, thus reducing the memory burden on any single GPU. So if you want to have a deep dive for Ben, for example, 3 papers I would like to recommend. The official Pytorch documentation about introducing Pytorch fully sharded data parallel API. Here you have from March 14, 2022, and they tell you exactly how it works for data parallel processes used in Pytorch. They give you some code examples. So if you want to have a deep dive, if you need this, if you are into distributed GPU computing, this is number 1. Number 2 would be from Hugging Face here, Accelerate the LLM training using now exactly this FSDP. This is from May 2nd, 2022. And there you have also how you can set up here your FSDP config file, your computer environment, everything that you need. You go with multi-GPU FSDP, and they give you here all the code examples that you need. And if you want to see this on action here, the third one is also from Hugging Face, fine-tuning Llama 2, 70 billion, so a huge one, using exactly here Pytorch FSDP from September 13, 2023. And here you have all the latest advancement and the latest tricks here to see here a Llama 2 70B model applied here. They tell you exactly the hardware, how you start all the notebooks and everything out of the data set, the prerequisite, the fine-tuning, the problems they encounter, and. So you have here a deep dive, takes about, 2-3 days to really get familiar with this, but please only do this if you're really working on a distributed GPU cluster, so a node, for example. Great. Those are the 3 papers I would recommend here to get familiar with this. As I told you, here are the configuration files for our particular fine-tuning code. And here on the left side, I give you FSDP. This is the complete config file for FSDP. And here on the right side, you see here the distributor type DeepSpeed. So these are the parameters you have to define for your particular configuration. Now, I'm not an expert here when to use DeepSpeed and when to use FSDP. So I asked Google Bart, and Bart told me, hey, DeepSpeed is a good choice for training larger model on more devices, on more GPU, while FSDP is a good choice for training even larger models on fewer devices. Now, if you are an expert and you work with DeepSpeed and FSDP on a regular basis, please leave us a comment in the description of this video. Would you agree with what Google Bart tells us, or would you have other experiences? That would be great to have some feedback on this point. Great. Talking now about optimization, memory reduction. You know, we have from the methodology, also we have a parameter efficient fine-tuning with a quantization. So we have parameter efficient fine-tuning, and we use here one methodology. This is the low rank adaptation, and we use here the quantized version. So if we do the same thing, we use StarCoder 15 billion free trainable parameter, and now we use not the full fine-tuning, but the quantized LoRA. So our trainable parameters now from our 15B model reduced to just 110 million LoRA parameters. So this is great because suddenly in our LoRA model, our trainable tensors are just 0.7% of our classical StarCoder 15B model. Yes, you can think about how much memory you need. If you apply flash attention to gradient checkpointing, you take into consideration everything you need to do. The total memory occupied by the model is now a single one A100 and just a 40 gigabyte, not an 80 gigabyte. So because our complete memory requirement is about 26-27 gigabytes. Long sequence length of 2K and batch size of 4 for training leads to higher memory requirements. Remember, compared to the full fine-tuning VRAM, this was close to 250 gigabytes. Now we have only 26 gigabytes. This is great. Yes, I know, unfortunately, it does not fit on a 4090, but on a single A100 40 gigabytes. So this is really cheap. Yeah, by the way, I seen here in the documentation of this that they say, hey, the A100 GPUs have a better compatibility with flash attention 2. And I've seen that, let's say, classical gaming GPUs do have compatibility problems when you apply flash attention 2. So careful, there seems to be an issue with flash attention 2 and let's say, professional data center, the latest NVIDIA cards. End of part 1. Next video, fine-tune Copilot part 2.